Hi guys, so you are in Ask Teacher J channel, and for this video I will be showing to you a solution or showing to you my solutions for an example problem related to heat effects of mixing. So the question for this word problem, by the way, I got this word problem from Introduction to Chemical Engineering Thermodynamics 8th edition by Smith and Van Ness. So the question is, what is the heat effect when 75 kilograms of H2SO4 is mixed with 175 kilograms of an aqueous solution containing 25 weight% H2SO4 in an isothermal process at 300 Kelvin? So, as discussed by your instructor or from your previous knowledge on heat effects of mixing, for isothermal mixing processes, what will be required is the heat released or absorbed after mixing the two inlet streams and then obtaining a particular concentration of the mixture in the outlet stream at a specific temperature. So of course, what you are going to do in this case is first establish the material balances for this one. So you need to know what is the total amount of the outlet stream as well as the composition of the species found in the outlet stream. Second is to perform an energy balance. Of course, for this one, this is a mixing process. If you can recall your knowledge in your chemical engineering thermodynamics course, there are many components or many energy forms of energy involved in a particular process, but we are going to simplify everything by assuming that the kinetic energy, shaft work, potential energy have no significant effects on the heat effects for mixing processes. So you will just assume that kinetic energy, potential energy, and shaft work will not affect the mixing process or the heat effects of mixing. So I think we can start with an overall balance. So OMB, or we call this as an overall material balance. So for this one, this is okay. So it's not in terms of rates, but we can consider this one as M1 plus M2 to form M3. Not really to form, but to produce the outlet stream of M3. Okay, for this one, alright, so this is 75 kilograms plus 175. Should I copy the correct values? Alright, and then of course the value of M3 for this one will be 250 kilograms. So the mixture that is formed is equal to 250 kilograms. So actually for this one, you're not required to since this is not per second basis, this is probably considered as a closed system. You just mix the two streams, but I just decided to use arrows for me to be guided by the inputs and the outputs or the expected outputs of mixing these two components. For the component mass balance, so this will be in terms of H2SO4. For the CMB or the component mass balance, um, I will be making use of X1. Is it okay to use X1? Yeah, I think it would be good if I will not anymore add a lot of variables. I'll just write or multiply the mole fraction to the total mass, not mole fraction, weight fraction to the total mass of the incoming stream. So for stream number one, I think I just need to write it to formalize everything. I'm actually doubting as to whether I need to write the symbols or not. But anyway, I just wrote it. So for W1, the weight fraction of H2SO4 here in this case is 1, right? This is pure H2SO4 in stream number 1. For stream number 2, okay, let's remember the mass, 75 kilos. And for stream number 2, it was specified that 25% H2SO4, okay, is present in the second incoming stream. And your mass is 175. Mass 2 is 175. So your unknown here is your W3. So what is the weight fraction of your okay, what is the weight fraction of your outgoing stream? So to solve for this one, I think it will be easy to trace. I need to rewrite everything for those students who somehow have a hard time in, you really need to see the nitty gritty of uh, the solutions. For this one, the weight fraction of your mixture plus 0.25 times 175, 250. This is equal to 0.475. So you have 47.5 weight percent H2SO4 in your outlet stream. Okay? We are done with the material balances. Let's now proceed to the energy balances. For the energy balances, we need the help of energy balances. We need the help of the enthalpy concentration diagrams. So for this one, let's have the total. We have here H or M1 multiplied by the enthalpy, because our enthalpy here is per mass basis. So I actually prepared here two diagrams. The first diagram, if in case we will be required to use the one found in Smith and Vaness textbook. There are only three isotherms present here. And later in the second example, we are going to use the diagram presented in the textbook of Sandler for the enthalpy concentration diagram sorry, of sulfuric acid. So this will be M1H1 plus M2H2 is equal to M3H3 plus Q, or this will be the heat effect. So for H1, I think 300, okay. So everything is maintained at a constant temperature of 300 Kelvin. So in your problem solving, you just need to focus on this graph over here. This is the isotherm for 300 Kelvin. So just focus your attention there, and then you can solve already for the heat effects because this is isothermal. So for M1, that is a pure H2SO4. For a 100% H2SO4, it was emphasized earlier that for this case at 300 Kelvin, the value of your enthalpy is more or less equal to zero. Okay, it's an arbitrary assumption. So you are going to apply that one. So we have the value of 75 kilograms, and we don't have the value for it because in our diagrams, it was arbitrarily set to 0 for pure substances. What's the unit again? Kilojoule per kilogram. And for M2, the value is, I think, 175 kilograms. Oh, I fear that the space might not be enough. So I will just move this one to the side. For H2, this is 25 weight percent, I think. I detect, okay, 25%. So we will go to the diagram, and the 25% is or has an enthalpy kilojoule per kilogram value of here. Okay, for purposes of demonstration, I will just estimate this one. 150. So for the purposes of, you need to actually have to do linear interpolation for this one. So you need to know what exactly is this value using a ruler. But for purposes of demonstration, please allow me to just estimate it. Okay? For 25 weight percent, this is 25 weight percent. This is 150 around here. So I'll assume this to be negative 125. Okay, thank you for understanding. So negative 125 kilojoules per kilogram. And then for M3, so the value that we have obtained for M3 was 250 kilos, 250 kilograms. And the value of W3 or the weight fraction is 0.475, which is 47.5. So again, you need to actually, in the actual problem solving, you need to actually use a ruler and a calculator to do linear interpolation. But for the purposes of demonstration, I'll just estimate it. So this is 45, so around here. And then I need to extend to 300 Kelvin. This is, by the way, 47.5 weight percent or 0.75. So at that value, my okay, it's really close to 300. So I'll just assume this to be negative 295. Okay, crudely. Okay, negative 200. So please do your own proper interpolation when you solve it by yourself. Okay, so what's the value of your Q? So for the first term, we can just cancel this out because this is 0. For the second term, we have 175 times 125 or negative 21875 kilojoules. Then for this one, we have, okay, 73750 plus Q. Alright, for this case, okay, just transfer or just do the mathematical manipulation. Negative 21875 kilojoules and then minus 73750 kilojoules. Okay, the answer is negative 95,725 kilojoules. Alright, so what can you infer from this one? The process is exothermic. Okay, it releases this amount of heat. For, yeah, so the values are actually in big numbers. I mean, 75 kilograms and 175 kilograms. So you would also expect that the value of heat released is also big. Okay, so this is an exothermic process. All right. Okay, so I think the time is, I mean, I just answered this very smoothly. So I don't want to stop the video recording, and I'll just continue and proceed to the second example that I plan to demonstrate for this video. So this is an open system. Again, this is a closed system, but I just decided to somehow present this as an open system for me to easily map out the inputs and outputs of the system. Okay, so for this example, a continuous flow steam heated mixing kettle will be used to produce 20 weight% sulfuric acid solution at 65.6 degrees Celsius from a solution of 90 weight% sulfuric acid at 0 degrees Celsius and pure water at 21.1 degrees Celsius. Estimate letter A the kilograms of pure water needed per kilogram of initial sulfuric acid solution to produce a mixture of the desired concentration. For letter B, we need to solve for the amount of heat needed per kilogram of initial sulfuric acid solution to heat the mixture to the desired temperature. And letter C, the temperature of the kettle effluent if the mixing process is carried out adiabatically. For letter B, this will be an isothermal process. For B, it's isothermal, while for letter C, it will be adiabatic, as mentioned in the last word of this item. Okay, for letter A, I think we need to have a mass balance. Alright, so there are no given values for the incoming and outgoing streams. So we will just, I think we can use a basis for this one. But the required here is kilograms of pure water per kilogram of initial sulfuric acid solution. So this is basically just a ratio. Okay, so if you're going to assume that the mass flow rate that will enter in the mass flow rate of 98% sulfuric acid is M1, and this is M2 dot, this is M3 dot, no values are needed. We just need to solve for letter A, this is just basically M2 dot over M1 dot. So you just need to solve for that value. And I think we can do that. Um, actually, I'm planning to solve this one without, this is really a very raw recording. So I'll just solve it accordingly, spontaneously without necessary preparations. So what I plan to do for this one is I will just organize my solutions based on what I have discussed, which is in the previous example, which is first establish the material balances and establish energy balances. Okay, to produce. Okay, all right. So let's start with uh, yeah. Let's start with OMB, or overall mass balance, or overall material balance. So very simple, similar to the example earlier, but this time we are going to use flow rates. That will be it. M1 plus M2 dot equals M3 dot. We don't know the given values of the three streams, but we do know the values of their H2SO4 weight fractions. So we are going to do CMB, or component mass balance, based on H2SO4. So for this one, we have so we have W1 M1 dot plus W2 M2 dot is equal to W3 M3 dot. For this case, for W1, that is 0.90 because that is 90 weight percent sulfuric acid, as you can see here. For W2, this is pure water. So there is no sulfuric acid present in this stream. So we can actually just place a zero for that one. And lastly, for W3M3, we have 20 weight percent. So the goal is to have a 20 weight percent solution. So 0.20 multiplied by M3. So this will actually result to an equation or a relationship between M1 dot and M3 dot. Okay, so I plan to get the value of M3 because this is what I want to cancel out later. I divide both sides by 0.20. So 0.90 divided by 0.20, and I have 4.5 M1 dot is equal to M3. Or essentially, M3 is equal to 4.5 M1. Now, what is required actually in item A is M2 over M1 because it's the kilograms of pure water needed per kilogram of initial sulfuric acid solution, which is the M1. So I will be using this equation over here. I will substitute the M3 equals 4.5 M1 in this part of the equation to get my M2 equals M1. So I'll try this one if this works. So we have, therefore, M1 dot plus M2 is equal to, the meaning of M3 as mentioned earlier is 4.5 M1. So it's 4.5 M1. So I will move the M1 here on the other side. That will be M2 is equal to 4.5 M1 dot minus M1, and that will be 3.5 M1. So if I'm going to get M2 over M1, so yeah, you are just going to divide both sides by M1 dot, and your answer will be 3.5. Okay, so that's it. That's my item A. For item B, it will somehow take a long time to uncover what are the values of H1. Not really long time, but I just need to watch and look at the diagram. And again, do my estimations because it's not really easy to read diagrams in a virtual blackboard. For item number 2, for H1, according to the data here, 98% sulfuric acid at 0 degrees Celsius. So let's look at an isotherm for 0 degrees Celsius. We have this one here. This one, if you can see there. And we are going to read for 90 weight percent. 80 around here. And then I'm going to stretch it more or less 150 or negative 150. So my H1 value is negative 150 kilojoules per kilogram. And for my H2, this is pure water. Hopefully, it's also zero. So, pure water, so 0 weight percent. But the temperature is not 0 degrees. but at 21.1 degrees Celsius. So I need to look for an isotherm that is here. So for this one, this is zero weight percent H2SO4. This is pure water in this side of the diagram. I would like to assume I'm actually using 21.1 isotherm, so please take note. So this is actually negative 98 kilojoules per kilogram. Okay. No, it's positive 98 rather. Apologies. It's positive 98. So this one, okay, okay, negative. This is positive 98. 98, that is just my estimation. And for H3, oh, I forgot the given. 20 weight percent at 65.6. So 65.6, the isotherm is this one. And I will need to know the 20 weight percent. 20, so this is 20 weight percent. I need to stretch this out. More or less 100. More or less. I'm not so sure if I got this right. I just use 100, guys. 100 kilograms per kilojoule. So again, we just do the same thing that we did earlier. M1 times H1 plus M2 times H2, and then is equal to M3 dot H3 plus Q. You don't know the value of, I know the value of, okay, I think I can solve this one. Based on M1, let's just use M1 data. So I don't know the value of M1 dot, but I know the value of H1, which is negative 150. M2 here is also unknown. The data is 98, positive 98 kilojoules per kilogram. I will not write anymore the, units so that I will be faster in terms of solving. But if you are my student or if your teacher requires you to write everything, all the units, you have to write everything. Okay. Okay, next. For this one, earlier I knew that I knew that this one. I knew that M2 dot is equal to 3.5 M1 dot. And I also discovered earlier that M3 dot is equal to 4.5 M1. So that I will substitute those values. So M1 dot negative 150, 3.5, 3.5 M1 times 98 is equal to, the value of your M3 is 4.5 M1 times 100 and then plus Q. So you can actually divide um, you can actually divide both sides by M1. So in that case, that will be negative 150 plus 3.5 times 98 is equal to 4.5 times 100 plus Q over M1 dot. So, to solve this, I think I can transfer this one. That will be negative 150 plus 3.5 times 98 minus 4.5 times 100 is equal to Q over M1 dot. That's essentially the, how do you call this? The heat per kilogram of initial sulfuric acid. So negative 115 plus 3.5 times 9.8, 98 minus 4.5 times 100. Negative 257 kilojoules per kilogram. Yan. What's the question again? Uh, amount of heat. I'm correct. Amount of heat needed per kilogram of initial sulfuric acid. So this is essentially the correct answer. So initial sulfuric acid. So Q is equal to Q over M1 dot is equal to negative 257 kilojoules per kilogram. Hmm. All right, there. So that's the answer for item B. For item C, okay, you will require a graphical approach for this one. So we need to know what is the temperature of the kettle effluent if the mixing process is carried out automatically. So the 65.6 is only applicable if the process is isothermal. What if the Q is equal to 0? You will expect that your temperature will not be 65.6. It can be greater than 65.6 or less than. So for adiabatic mixing, this is what we are going to find out. If the value or the final temperature will increase in value or will lower in value as compared to isothermal process. We need to use a a graph for this one because we are actually going to make a line in the diagram and find out what temperature will the what final temperature will the mixture be if the process is adiabatic? That means you are not going to allow energy to come in. You're actually also not going to allow the energy to come out to maintain a temperature. So the temperature will change in response to the adiabatic process. So for this one, what you're going to do actually is to plot where is the 90 weight percent at 0 degrees Celsius located in the enthalpy concentration diagram. For this one, you are going to delete, okay, delete all the. So the 90 as presented earlier, what was that? 0 degrees, right? So here, there. So I'm assuming it's there. Okay, so, alright. And this is the one, or the stream one. The stream number two is water 21.1 degrees Celsius, 0 weight percent. So 21.1 isotherm here and 0 here. Okay, now you are going to create a line, okay, connecting the 2 points. So give me a shape. So I'm going to create a shape. Actually, I cannot. I don't, I don't know if I can really hit this one correctly, but okay. I'm still confused if I'm going to really, how will I know if the drawing that I made is correct? Okay. Okay, I'll have one last try. Still, I cannot make it. So I will manually draw it. I don't have a ruler with me. Just have my comb here. I just my comb to guide me. Okay. I'll just use the other side. So I'm basically connecting the two. Oops. So I will connect the two. This is actually actually a very crude. If you can see, it's not perfect. I just used my comb here. I don't have my ruler here, unfortunately. I thought the lines here in the shapes option in Microsoft OneNote will give me a very accurate connection between point 1 and point 2. Now, the point 3 or your output stream has a fixed composition of 20 weight percent. So that is what you're going to set in your enthalpy concentration diagram. So the 20 weight percent is here. So you're going to extend that line, make a line here, okay, and then touch that one here. Right. Now the question is, what is the final temperature of my, how do you call this? What is the final temperature uh, of my outlet stream? Okay, after ensuring that the process is adiabatic. So actually what you're going to do, guys, is to read the isotherm wherein this point will touch, because this is the point wherein the mixing will happen or will take place. For an adiabatic process, this is actually the step 3 or the output stream 3. Unfortunately, we were not able to touch an isotherm, but we know that this is in between 37.8 and also in between 65.6 degrees Celsius. So the final temperature is actually in between 37.8 degrees Celsius and 65.6 degrees Celsius. So that's actually the expected value. Now, for the interpolation, I think we can actually interpolate this one. You just use your ruler, no? Use linear interpolation. My interpolation, if I'm going to solve this, my approach will be to read it since this is going, since the line is, the isotherm is expected to be here, right? So what we can actually do is to, um, the perspective will be in this direction. So that means you are going to put your ruler in this way. So you have your ruler situated in that location to measure the correct. It should not be, um, I think it's wrong to have your ruler oriented in this location. Okay? Because it will actually create a big deviation in terms of the values. Okay, it will give you actually a wrong interpretation. So you just have to, yeah, the ruler should be situated in this one, and then perform linear interpolation to know if, or to know the value of your final temperature. Okay, so you must have an imaginary isotherm for this one because you don't have enough data. So you just assume that okay, it's in between 37.8 and 65.6. So right now I can just assume it's around 45 degrees Celsius, but actually I'm not sure. Okay, but the final answer that I can give is around in between. The safest answer will be in between 27.8 and 65.6. So I hope you were able to understand how you're going to use the graph to solve for the final temperature for an adiabatic mixing process. So that will be all for today. Thank you so much for watching my video. If you have any questions, you can email me or chat in the comment section, and then I will answer it if I have time. Thank you so much, and I will see you in my next video. Bye, guys.